thanks. Thanks for coming back. That's really nice. So what I didn't mention is that if we have time, then we will have an interactive quiz at the end. So this is the QR code, but I will show the QR code at the end. And then we will have a short quiz so that to make it more interactive. Okay? And there will be a prize, possibly. It depends whether there is time. Okay. So lattice-based zero knowledge proofs, part 2. So far we consider this nice equation, AS is equal to U, and this equation was over RQ, right? And in the end, we only managed to prove somewhat this relaxed relation. Okay, so we managed only to prove that we know some short S and short C, such that AS is equal to CU. And we also have seen that this is fine for identification schemes, signatures like the lithium, and in general, we can get pretty small sizes. Okay, so this part of the talk is about what we wanted to do at the very beginning. So at the very beginning, we wanted to prove statements like AS is equal to U, S has ternary coefficients, and this equation is over integers, over ZQ. Okay, so it's not over the polynomial ring, but it's over ZQ. Okay, so that's, so how can we do that? And why is it interesting? So we want to prove exactly. So we really want to prove that S lies within some specified range, and AS is indeed equal to U, mod Q, not C times U. Okay? And this is really crucial if you want to build more advanced privacy-preserving primitives, like if you want to encrypt something and we want to prove that this encryption has been done correctly. Okay? We want to prove that we know that our vote was either 0 or 1 and not between -100 and 100, right? So it has various applications in more exotic signatures, ring signature, blind signatures, and so on. But in general, this leads to much bigger proof sizes. Okay, so this part of the talk will focus on how to prove this type of statement efficiently. And this will be based on the work that I was part of in 2022. Okay, so just to make it more concrete, I will focus on the linear equation, so AS is equal to U. And for simplicity, let's just say I want to prove that it's binary, okay, 0, 1. Okay, and if we want ternary, we can just binary decompose and so on. Or like, yeah, if you want to prove Euclidean norm, it will be the same strategy. But just to have something concrete, I'll just stick to binary. Okay? So later on, we also have the quiz, applications, and maybe a little bit about how we can, how these techniques are used to obtain succinct proofs. Okay. So I discussed the main goal, right? So the main goal consists of 2 parts. AS is equal to U mod Q, and S is binary. So let me just focus on the second part for now. How to prove that it's binary? What we will do is that we will show that proving binary is the same as proving inner products over integers. Okay, so we have this very simple lemma, which says that if we have a vector which is over integers, then it's binary if and only if the inner product of S and S minus the 1 vector is equal to 0 over integers. Okay? So why is it true? Well, the first direction is trivial, right? If it's binary, then each term in that inner product is 0. Okay? But so suppose the other direction. So suppose that the inner product is 0, okay? So we can write down this inner product as a sum of these quadratic terms, Si times Si minus 1 is equal to 0. But now, since each Si is an integer, we know that Si times Si minus 1 is at least 0. It's greater or equal to 0, right? Because Si is indeed an integer. So in particular, the sum is equal to 0 if and only if each of these inequalities is an equality. So in particular, Si is either 0 or 1. Okay, so that's a very simple lemma, but we will show that it's easier for us to prove inner products. So any questions so far? Okay, so that's the first step. So now I want to prove that AS is equal to U mod Q. And now the next observation is the fact that the inner product is equal to 0 over integers if it holds mod Q. So S, the inner product of S and S minus 1 is 0 mod Q. And the norm of S is much smaller than Q. Why is it the case? So this is true because, yeah, obviously from the top to bottom it's clear, right? But if it's from bottom up, we prove that the inner product of S and S minus 1 is 0 mod Q, and we prove that if we pick sufficiently small, parameters, then we can make sure that this equation has no modular overflow. In particular, this holds over this equation holds over integers. Okay, so now we have 3 parts to prove. The linear equation AS is equal to U. The inner product S and S minus 1 is equal to 0 mod Q. And the norm of S is much smaller than Q, intuitively. Okay, so remember that I started with S, which is binary. But in the third column, I just want to prove that it's somewhat short. So this relaxed thing is fine for me. Because if I know that it's like relaxed short, then combined with all the other equations, I can make sure that there is no modular overflow. Okay. So I will call the first one the linear proof. The second one is the inner product proof, and the third one is approximate range proof. So that's what I call the third one. And I will focus on the approximate range proof first. Okay, so how to prove that S is somewhat short? So the idea is the following. If I take a random short vector B, then honestly, if S is short, then the inner product of B and S is short, right? But if I am given a large vector S, so suppose I'm cheating, I have a large vector S, then what's the probability that the inner product of B and S is short? And now if I even want to consider zero knowledge and want to somehow mask the inner product of B and S, because who knows, the inner product of B and S could reveal some information about S. So if I take a short mask Y, then obviously Y plus the inner product of BS is short if S is short, right? But now, going back to the same question as before, if I have a large vector S and I want to cheat in some way, so even if I have a large vector S and Y, then what's the probability that Y plus the inner product of B and S is short? Okay? And to answer this question, we will focus on the following lemma. Okay, so the lemma says that if I just fixed any B and S, so any S and Y, and I sample a random binary vector B, then the absolute value of the inner product of B and S plus Y being less than the norm of S divided by 2 is at most 1/2. So in particular, what this lemma says is that with probability at least 1/2, if the image the inner product of BS plus Y is short, I'm always confused which direction. So if the image inner product of BS plus Y is short, then we must have that the norm of S is also short. Okay, so we focus on this lemma. I give a brief proof sketch, and then we can jump on to questions. So how to prove this? So to prove this, let's say, okay, so infinity norm, right? So the norm of S is equal to Si for some I. Okay, so then I can write this this term Bs plus y equal to bi times si plus r. And we don't care about r. We really care about bi si and the term bi. Okay? So simply by the triangle inequality, at least one of r and si plus r, which here denotes when bi is equal to 0 and bi is equal to 1, at least one of them has to have norm at least the norm of s divided by 2. Why? Because if it wasn't the case, then by triangle inequality, we would have found si, which has norm less than the norm of s, which is contradiction. Okay? And the probability of hitting that value is at least 1/2. So that concludes the proof. So now this, maybe you can say, okay, this lemma is kind of useless, but now by kind of repeating this experiment, let's say lambda times, I get that if I have any s and y, with an overwhelming probability, the norm of bs plus y must be bigger than the norm of s divided by 2. So in other words, to be very informal, I want to say that if, with an overwhelming probability, if bs plus y is short, then the norm of s must have been short. Okay, so that's the key strategy for the approximate range proof. Any questions about the idea? Okay, so let's move on. So let's map this intuition to some kind of protocol. So I have this binary vector, right? And I want to prove that it's somewhat short. So the idea would be that, I mean, obviously it's not zero knowledge, but say the prover samples some mask y and outputs y and s. Yeah, obviously it's not zero knowledge, right? But just the intuition would be that the verifier picks this challenge matrix B, which is the random binary matrix, and the prover will output z equal to y plus bs, and some rejection sampling as usual. Okay? And then the verifier checks that the norm of z is short, and it just checks manually that z is equal to y plus bs. So what that lemma says, I mean, obviously the verifier could just check, okay, is S binary, right? I mean, they could do that directly. But the main point of this protocol, which is useless, is that if Z, which is equal to Y plus BS, is short, then it must be the case that S was short as well, using the lemma from before. Okay? So now, this, that's the intuition to prove why S is somewhat short. Okay, and now this is kind of a useless protocol. How can we make it more interesting? Well, instead of, okay, so that's what I said. So then the verifier is convinced that the norm of S is at most 2 times the norm of Z with high probability. Okay, yeah, so this says that sending Y and S is pointless because it breaks zero knowledge and so on. So now we want to deal with this by using commitments. So commitments were already introduced. Also yesterday, you've seen the construction of the I-type commitment. So just to recall, the commitment scheme, in the commitment scheme, I want to commit to a message under some randomness. And binding says that it's hard to find 2 different openings for the same commitment, very informally, and hiding says that the adversary cannot learn any information about the opening from the commitment, okay? So we will use these binding hiding commitments in this particular case. Okay, so instead of sending S, Y, and S, so for simplicity, but I will explain later, I will use the same randomness R for all commitments, okay? So I commit to Y using randomness R. I commit to S using randomness R. Sure, to make it hiding, my randomness will be long enough to cover that. But I commit to Y and S. Okay, I get the challenge B. And yeah, so this attempt is also pointless because I sent S, Y and S as usual. But now I send it after getting the challenge. Okay? But by the binding property, the binding property makes sure that Y and S that I receive will always be the same. So it's kind of already fixed, because I already sent the commitment T, the commitments TY, TS, before seeing the challenge B. Okay, so now, instead of sending all this sensitive information, we will prove knowledge of Y, S, and R, which satisfy all the verification equations. Okay? So so that's a standard strategy, that instead of sending all the sending the witness, or like sending in the information, we prove knowledge of them. Okay, so what's going on is that I will commit to Y and S. The verifier sends B. I output the Z, which is this image Y plus BS. We make sure that the norm of Z is short. And then later on, I delegate the proof to proving knowledge of Y, S, and R, which satisfy all the commitment relations, and Z equal to Y plus BS. Okay? So at the end of the day, I reduce proving the approximate range proof to proving knowledge of a commitment opening together with a linear proof. So now, what I have left is basically inner products everywhere. So linear proof, it's an inner product between a public vector and the secret vector. The second one is between the two secret vectors, and the third one is between the public and the secret vector.
So previously, when I mentioned this subdelegation, we said, yeah, but then we are kind of using a generic framework, and that's something we want to avoid. And I have an impression that when we have this subroutine to prove knowledge of the commitments, we're actually doing the same thing, that we're using some general purpose framework.
I'm not done yet, so I'm just continuing the protocol.
Right.
This is a very complicated protocol. I mean, not too complicated, like a 9-round protocol, and you'll see where I delegate this to the next step. So now we're interested in proving inner products. Okay? So there are all these inner products here. I want to prove inner products. So the next step is proving inner products over ZQ. Right? So we want to prove inner products either between two committed messages, or one secret, one public, and so on. As we discussed before, if we work over integers, will result in a bad soundness error. Okay, so we still want to use the polynomial ring because it gives us nice soundness, but we want to prove statements about integers. So in a way, we need to translate inner products into relations over the polynomial ring, so that we can prove these relations over the polynomial ring with good soundness. Does it make sense? Okay. So now we go into the details a little bit. So I have this standard RQ, and then I define these nice functions. So sigma i's, the automorphisms, which are defined if I take take an x, then sigma I of x maps to x to the I. Okay, so if I have a ring element, then I map all the it's an automorphism, so the constants are out. Then I map x to x to the I, x squared to x to the 2i, x cubed to x to the 3i. Okay? And in this talk, I will only consider about the so-called conjugate. So I will focus on the sigma, so the function, which is sigma minus 1. So it maps x to x inverse, x squared to x to the minus 2, and so on. Okay? And also for notation, I will denote the constant term of x to be the constant coefficient or the constant term of the ring element x. Okay, so that's the setup. So what we will do is that we will translate proving inner products over integers to proving statements about ring elements. So how do we do that? So the key ingredient is the following lemma. So if I have two ring elements, so I have the ring element U, and I just write it out, and I have the ring element V with coefficients Ui, Vi. Then if I look at this, this weird product, which is U times sigma of V, then actually the constant coefficient of that is exactly my inner product that I want to, that I'm interested in. Okay, so this lemma says that I can transform proving inner products to proving statements about constant terms over the ring. Okay, so that's like one more step towards our goal. So how to prove it? Yeah, so it's just writing it out. So if I have U times sigma minus 1 of V, then I have, that's my U. Now I'm applying sigma to the whole V. It's an automorphism, so I have this U as usual. And here I'm applying sigma to each x to the I. So I have VI x to the minus I. And then if I multiply all these things, I have the sum of ij, ui, vj, x to the I minus j. Okay? And now if we're interested in the constant term, then you can see that the constant term is indeed, you know, u0, v0 plus u1, v1, and so on. So that's the inner product that we're interested in. Okay? Any questions so far? Yeah.
So this week gives the reason why we have a sample. Do I see it correctly? So the reason why we have a sum of d terms is because there are d choices for I and j in this range where they have the same value and become 0 and yeah.
Yeah.
Okay.
Okay. So how can we apply this lemma in our case? So the application would be that, okay, I want to prove that the inner product of S and S minus 1 is 0 mod Q, right? And now using this lemma, we can write it as, yeah, it's not a nice formula, but we need to prove that the constant term of S minus the sum of all the powers times sigma of S is equal to 0. Okay, that's literally the application of the lemma. And then to extend it to multiple polynomials, or to a vector of polynomials, I can just do it like component-wise. Okay, so I have S, I have a vector of length m, and I just divide it by, you know, to obtain m over d subvectors, and I apply each of them with this lemma. Okay, so I have this particular term. So the details are not very, are not very important, but it's just what to keep in mind is that we know how to translate proving inner products to proving statements about ring elements over RQ. Okay? So back to the overview. We had these things to prove, and now applying all these, applying this lemma, everything boils down to proving certain equations over RQ and proving that constant terms are 0, for example. Okay, so like the middle one is what exactly it is, but then the left and right, I just say, okay, so there are some public functions, fi, gi. Okay, so now we reduce it to proving that constant terms are, let's say, 0. Okay, so I can combine all these things into proving this, right? So I just collect all these functions, and now I have to prove that a lot of these functions, the constant term of all these quadratic functions, because like this one is quadratic. I mean, these two will be linear, but this one is quadratic. But say I have many quadratic functions. When I say quadratic, there is also the sigma somewhere. So that's why I say with sigma. So I want to prove that the constant term of a bunch of quadratic functions is equal to 0. Okay, so how do we do that? So we want to prove the constant terms. Well, we can see that for any, if I linear combine all these functions, right? If I linear combine with all these functions with integers, or like ZQ elements, I will get that the constant term of the linear combination, because these mu i's are integers, I can put mu i's outside. So it's a sum of all the mu i's times constant term, which is 0. Okay, so that's nice. So that's for any mu1, mu k. But what happens if I try to cheat? If for some I, the constant term is not 0. Okay, but then one can easily check that, you know, the constant term, in this particular case, the constant term of the linear combination will be 0 with probability 1 over q. Okay, so that's kind of the probability of cheating. As we discussed before, we want q to be small, right? We want the q to be polynomial, so this is not enough. So that's why we need to repeat a few times. So that's what I call L. Okay, but like if q is, say, 2 to the 32, then we just need to repeat 4 times, so that's not too bad. So that's the idea. Okay, so the problem here is that if I linear combine things, and I just sum, if I send this linear combination, that it potentially leaks information about all the secrets we have. Okay, so we need to mask again. So how do we mask? What I do is that I know that for an honest prover, this linear combination, for this linear combination, the constant term will be 0, right? So I don't want to spoil that with my mask. So I will make sure that my mask have constant term also equal to 0. So it doesn't mess up the constant terms. Okay? But for other coefficients, I will mask. So I will pick uniformly random ring elements with a constant term 0. Okay? And now, given these challenges mu jk, I will send the linear combination plus my mask. So I will send the hj. Okay, so I will send all these hj. So there are capital L of them. Okay, so now by completeness, the constant terms of these will be 0, right? Because the constant term of these are also 0. And I made sure that the constant term of gj is also 0. So the constant term of hj is 0. Okay, and hj hides the information about other coefficients of this linear combination. So this is because we really picked all these g's uniformly at random. Okay? So then what's the protocol now? So the protocol will be that I will commit to these masks, G1 up to GL. Okay? I'm using the same R, as I said. The verifier outputs all these challenges, so random mu ji. And then I compute all these hj, which are gj plus the linear combination. Okay, so I output all these. And now the verifier checks whether the constant terms are 0, which holds by completeness. But now what we have left to do is that we need to prove that hj are well formed. So in particular, we reduce this problem to literally proving quadratic equations over RQ. So we want to prove knowledge of the opening together with a bunch of quadratic equations over RQ. Okay, so indeed, for now, we really switch to proving inner products over ZQ, relations over ZQ, to relations over RQ. And now, there is a bit more hope that we can use the fancy stuff from the polynomial ring, which ends up with small soundness error. Does it make sense? Any questions so far? Okay, so at the end of the day, we have to prove a bunch of quadratic equations. So, I mean, multiple quadratic equations. Can we? Oh, public quadratic equations, and we still haven't got rid of the sigma. So there are some sigmas around, right? So now, back to a simple exercise. The question is how to reduce proving multiple quadratic equations to a single one. So I'll give you 2 minutes to discuss the ideas how to do it.
Going to discuss the topic, but I have a request. So. Because you record this on the 15th.
Okay, so let's get back. Hope you had a nice discussion. So yeah, so the strategy is the same as before. We'll just linear combine. So we want to prove multiple quadratic equations. Let's just combine everything into one. Okay, so the verifier picks the challenge, all these L elements in RQ, random elements in RQ. And the goal now is to prove one single quadratic equation. Did anyone get that? Raise your hand. Some people. Okay. Yes.
Are we allowed to multiply just pointwise, and in this way we just end up with a single equation instead of multiple? Am I right? Or
sorry, could you repeat the question?
Could we just multiply pointwise the equations and end up with the single equation in the field, or am I wrong?
Multiply pointwise all the equations.
For example, we can multiply pointwise s and y. After that, multiply pointwise to g using one of the previous lemmas.
So the question. So the pointwise.
We just could multiply s with y. As far as I know, they are polynomials, and
you mean pointwise, meaning like the first component of s with first component of y?
We just got lemma before. Unfortunately, I forgot how it's properly called.
Like the one with inner products?
I think earlier.
This one? Or the previous one?
This one.
Okay, sure.
Can we use it?
Sorry?
Can we use this approach?
Oh, this approach was to map the equation over ZQ to an equation over RQ. And now we are already in RQ everywhere. So now what we have to prove are these quadratic equations over RQ. So all these things are like quadratic equations over RQ. Does it make sense?
I think yes.
Okay, hopefully if it gets resolved later, but I'm happy to talk if anything's unclear. Maybe we can discuss offline if that's okay. Thanks.
Or possibly I maybe got something wrong, but okay, let's discuss it offline.
Any other questions? Yeah, there is a question here.
I think the multiplication point-wise will give you or, not and. And the question was about and, so both should.
Let's use the microphone.
So I think the proposed multiplication would give you or instead of and. So we'll tell you that first is 0 or the second is 0. Most probably.
I guess we can discuss this offline. Okay, so now from proving multiple quadratic equations, we end up with just one. Okay? So now what's the probability? So now we wanted to prove multiple quadratic, right? So in particular, what's the probability, you know, if a cheating prover wants to come up with some S, Y, and G such that for one of them it doesn't hold. Okay? Then what's the probability that we end up with, with the linear combination being 0 for random coefficients, mu j, if one of the equations doesn't hold. Okay? So now, for simplicity, if I pick modulus nice enough like Q being 5 mod 8, I can write it down as, by the Chinese remainder theorem, I can write it down in this way. So in particular, RQ is isomorphic to a direct product of two fields. Okay? So we have this. And then the probability that one can show is that if for any x, the probability if I pick a random mu j, and if this is non-zero, if this is non-zero, meaning that up to isomorphism, one of those components is non-zero, is equal to x, is at most q to the minus d over 2. Okay, so that's a little bit more technical stuff. So yeah, but in general, to analyze this probability, we need to dive more into the structure of how RQ looks like. Okay? So yeah, but the idea is, as before, so the main takeaway is that if we have multiple quadratic equations, then we can just randomly linear combine them, and we end up with a single quadratic equation. Okay, so at the end of the day, we end up with a single quadratic equation here. And now how to prove that? Yeah, so it was all hand-waving, and I didn't mention what the commitment is, why it's the same R, but I guess we need to go to the details at some point. So now the first step is describing what the commitment is. So the commitment I'm discussing is the so-called ABDLOP commitment. So it's a combination of the I-tie commitment, which was kind of shown yesterday, and another one which is called BDLOP. Okay, so what is this commitment? We want to commit to a message which we can split into two parts. So the first one is S1, which we require to have small norm. So it has to be short for binding. Okay? But then there is the message M, which it can be arbitrarily large message. So in our case, just to give it some context, we can put S1 to be S. We can put S1 to be S. And in M, I can put Y and G. Possibly Y could be in S1, but for simplicity, let's just put it in the M. And especially this masking vector G, it will be large, right? So what was G? G was a random element over RQ with a constant term 0. So of course, it's going to be large. So we will put that G in the M part. Okay, so now how to commit? The commitment has two parts. The first one is, it consists of two parts, and the first one is the binding part. So the first part is TA, and TA is equal to A1S1 plus A2S2. This is literally the ITAC commitment from yesterday, okay? But now we have the second part, which deals with all the large norm elements. So TB is equal to B times S2 plus M. Okay? So if L is equal to 0, then there is no TB. So it's literally TA equal to A1S1 plus A2S2. Okay? And if M1 is equal to 0, then I end up with a BDLOP commitment. So that's for people who are more into this area. Okay? So this is more of a generalization. But the crucial thing is that if S1 is long, then it compresses S1 with a commitment TA. Okay? But it doesn't compress M, because you can see that the size of TB is the same as the size of M, because TB is literally BS2 plus M. Okay? So one can show that breaking binding implies finding a solution for A1, A2, which is the same, which is a very simple exercise. And then for hiding, we make sure that A2B times S2 is looks uniformly random. Okay, so that's this term. So this term makes sure that the whole commitment looks pseudo-random. Okay, so we have the binding, we have the hiding. So that's how we commit. Yes, we have a question.
So what is the randomness for the commitment? The B, or which parts are the randomness?
So the randomness thing is S2.
Ah, okay.
So the S2, and S2 has to be long enough that A2, B, S2 looks pseudo-random.
Okay, so these A1, A2, and B were part of some public...
Oh yeah, it's like...
Okay.
Right.
Just recalling how the... Okay, thank you.
Okay. Okay, so let's start with something simple, because it will be very similar to what we saw in the previous talk. It's the opening proof. Okay, so the opening proof is that we want to prove knowledge of S1, S2, and M, and S1 and S2 are short. Okay. So we will end up with the problem with the relaxed thing, but we will show how it's okay for our setting. Okay, so I want to prove this type of equation, and we will do with just like in the Schnorr in the lattice setting. So I sampled the masks yi. So now I'm pretty informal. I'm not putting all the parameters and rejection sampling. So I sample yi, so y1, y2. I compute w equal to a1, y1 plus a2, y2. So literally Schnorr. So now we send w. The verifier sends the c. And the prover outputs zi, which is yi plus csi. Okay? So literally the same thing as before. And the verifier has to check that Z1, Z2 have small norm, and A1, Z1 plus A2, Z2 is equal to W plus CTA. Okay, so the opening proof is somewhat similar to what we have with the identification protocol from the previous talk. Okay, so any questions so far? So that was just the opening proof.
So I just don't quite remember why is there only a single message in the first round? Like, why can we combine? I think you probably presented it in your first lecture. I just want to recall, like, why can we combine the first message, and in the third round we send two values. In the first round we just sent the W.
Sorry, could you repeat?
So why do we have just a single W in the first round and then two values in the in the third?
I mean, I would say that just consider this equation at the top. TA is equal to A1 S1 plus A2 S2. And now imagine that you think about the matrix, the concatenated matrix A1 A2 and the vector S1 S2. So for this equation, we're literally doing the same thing as before. But now the matrix is not just A, but A1, A2.
Okay. I think I see. Okay. Thank you.
Okay. And now suppose that we want to equip this with proving quadratic equation, okay? Without automorphisms yet, for simplicity. So I had this opening proof. I want to modify it to also prove some quadratic equations. So for simplicity, suppose we have one quadratic equation, which is just S1 transpose S1 plus M transpose M. Okay? How to do it? We have already seen the opening proof, W, C, and Z i's, right? And what we know is that the verifier, which knows Z1 and Z2, the verifier can compute Z1 transpose Z1, which has this following form. But the most interesting thing is that the quadratic term, the quadratic term of Z1 transpose Z1 has what we are interested in. So it has this S1 transpose S1. Okay? So that's nice. That's one of the things we want to prove. Well, we can't really do this for M because we don't send any Y plus CM, right? But then we can make use of the second part, the TB. So we know that TB minus BZ2 is minus BY2 plus CM. So that's by computation. Okay? So in particular, if I multiply TB minus BZ2 transpose, TB minus BZ2, I end up with some ugly quadratic equation, but the term inside the C squared is what we wanted to prove. It's the M transpose M. Okay? So now if I combine these two observations, so the left-hand side is what the verifier can compute themselves, but then it's a quadratic equation where in the quadratic term I have what I wanted to prove. Okay? So I want to prove that this term next to C squared will be 0. Okay, so now, yeah, so I have G0 and G1, which are kind of some ugly parts. Okay, so now, hence we commit, well, sending G0, G1 can reveal some information about our secrets because they somehow involve all these Y's, all these SI's, or these M's. So we need to additionally commit to G1. We don't need to commit to G0 though. So I commit to G1, which is the T1. So I expand this commitment with a T1. Okay? Okay, so so now if I commit to G1, then because T1 is equal to B1 transpose S2 plus G1, I can write CG1 as T1 minus B1 transpose Z2. So in particular, I can get rid of the CG1, and I have things which don't depend on C anymore. So we know that CG1 is equal to T1 minus B1 transpose Z2. So the left-hand side, that the verify can compute themselves, can be written as G0 plus B1 transpose Y2, which don't depend on C. Okay, so that's, but yeah, so there was this quadratic term, but it's 0, right? Because that's what we wanted to prove. So to summarize, we have this 3-round protocol where we have the opening proof, just like before. Okay, then we have some ugly terms. So I said we have the G1, I commit to G1, then I have this G0 plus blah, blah, blah. Some blah, blah, blah term, independent of C. So I can send W, T1, and V. I get a C, and I output the ZIs, just like before, and rejection sampling. Okay, and then the verification checks are the same. So checking that ZIs are short, A1 Z1 plus A2 Z2 is equal to W plus CTA. So that's all the opening proof. But additionally, to argue that the quadratic equation holds, we need this check, which I described before. So all the left-hand side is what we can prove, what the verify can compute. And the right-hand side was this resulting term which we send to help the verify to check. Yeah, any questions so far? Okay, so yeah, so it's a bit more complicated. Now another question is how to prove quadratic equations with the sigma, right? So that's another thing. So the idea is that if we assume that the challenge C is stable under the sigma automorphism, then it doesn't really change the strategy. So in particular, I can do all these. So suppose I want to prove this. So S1 transpose sigma of S1 plus M transpose sigma of M is equal to 0. Then I can compute literally the same strategy as before. And because I assume I kind of pick a challenge space so that sigma of C is equal to C, I still end up with a quadratic equation. Okay? So the strategy is the same. If we didn't have sigma of C equal to C, we would have various C and sigma of C flying around. So that's what helps. Okay, so for the challenge space, as before, we need an exponentially large challenge space. We want sigma of C to be equal to C. We want the difference of distinct elements to be invertible for the same reasons as before. So what we do is that we pick this nice challenge space, but I'll just skip it. But yeah, so it has this nice structure. So we pick this nice challenge space so that it's stable under the automorphism. And we will also show that, at least in this particular case, if it's stable and non-zero, then it's invertible over RQ. Okay, so that's, let's just skip it due to time. Okay, so in terms of soundness analysis, it will be similar as before. We do we first want to have 3 different transcripts with the same first message, but different CIs, so C, C prime, C double prime. And then we use some kind of interpolation to deduce the quadratic equations. Okay? The problem is that we still end up with this relaxed binding property, so this relaxed relation. So as before, we extract some candidate witness, so short divided by short. So it's just a candidate witness, right? So how can we deduce that it satisfies all these things? Well, that's the reason why we went through all these steps from the beginning. So we extract a candidate witness, which is not short, right? Okay. We prove quadratic equations and proving constant terms, so we can prove all these things mod Q. Okay? But then the important thing comes in the approximate range proof, which said that even though this is big, if that was big, it wouldn't have passed the approximate range proof part. So this makes sure that the norm of S is somewhat small. And combining with this, and showing that there's no modular overflow, we end up with proving that it's binary. Okay, so that concludes the extraction proof. So one comment, which D to pick. So D is the size of the ring dimension. So we want D to be large enough so that the challenge space is exponential size, right? So we want D to be big so that the soundness is fine. But on the other hand, we have some interesting parts of the proof, like sending the H's, sending H1 up to HL, where L is the parameter so that Q to the minus L is negligible. Okay, so if we pick D big enough, if we pick D too big, then this part will be expensive. So that's why we don't want to, we want to pick D big enough for soundness, but not too big for efficiency. So efficiency applications, let's just go through it. So this strategy that I proposed, that I presented, gives pretty nice sizes for proving such statements like LWE, which are around like 14 kilobytes, and beat prior lattice approaches, which are based more on like entities and also some hash-based constructions. Okay, and also from this we can build some nice applications like integer addition, multiplication, verifiable encryption, blind signatures, ring signatures, and so on. So these exact proofs are very interesting for and useful for this type of applications. So quit later. And so what about snarks? Well, so we have there is the nice proof system called Labrador from Crypto last year. What it does is that it starts with some generic statement, which is proving bunch of quadratic equations, bunch of inner products, which is then kind of similarly as here, it's split into a few parts, like approximate range proof to prove the norm, equations over ZQ, equations over RQ. Then there is a mapping for approximate range proofs to equations over ZQ, from ZQ to RQ, kind of just like here. And then there's a smart amortization so that we can go back. So then with Labrador, it's very efficient to prove very big statements can be around 60 kilobytes. The problem is that we don't have succinct verification, and yeah.
Sorry to interrupt. I was wondering, so in the previous... Sorry to interrupt you mid-sentence. In the previous setting, you were proving linear equations, right? Yeah. But a generic statement, it's not clear. You can always break it into sort of low-degree equations over ZQ and approximate range proofs and so on.
So your question is like, how can I transform like any NP statement into, so there's a so they have like this principal relation, which is about proving a bunch of inner products and norm bounds and so on, and then they prove how to reduce like from R1CS, for example. So from like generic.
Can you give some intuition, like how will you do it? So take an arbitrary statement, NP statement, right? And this can be arbitrarily high degree. How will I do it?
First, you would map to a language which is kind of used. I'm not sure if it's used anymore, but like to a rank 1 constraint system, which is basically you map it to some linear, some algebraic statement. So it's called rank 1 constraint system, and then from this to you go to this principal relation in Labrador. I'm not saying that this conversion is efficient, obviously, but at least in principle it can be done,
Okay. I can ask you more offline.
Thanks. So the reason why the succinct verification fails is that for approximate range proof, we have the verifier sends this matrix B, which width is exactly the width of the witness. So in particular, the verifier has to deal with this big matrix B. So if M is long, then B is also big. So if one uses approximate range proof, then, well, it's very likely that the verification is not that fast. So we had some ideas to possibly use some structured tensor type matrix to prove, to use approximate range proofs. Another idea is to somehow manage to use Labrador as a subroutine. So we use Labrador on a smaller statement so that the verification is linear size compared to this smaller statement, or just don't use approximate range proof. But then there are some problems with this. Okay? So yeah, so that's, I would say that concludes the talk.